Hello, class. This is Mr. Hart, and in this podcast, I want to go over the last part of the gravity and orbits chapter, which is orbits. Okay, so you probably already know what an orbit is, but if you think about it, it's the path of an object around a larger space body, right? So the moon orbits the Earth orbits the sun, okay? The sun orbits the center of the galaxy, okay? So all these objects orbit around each other, right? They have a path around a larger space body. Okay. And in class, we played around with a simulation called My Solar System. If you go to the PhET website, I recommend playing around with it. But one of the key ideas of a orbit is that it will orbit around or rotate around the center of mass of that orbit. Okay, so for example, in this picture, right, we have this little small planet orbiting the sun, okay, a larger space body. Because the sun is so big compared to this little planet, the sun is going to pretty much be the center of mass, right? Which is why the planet orbits the sun and not the sun orbiting the planet. Okay, but if you had two bodies that are about the same size, like in a binary star system, then they'll actually orbit around the respective center of mass. Okay, but let's think about how we came to know about orbits. Okay, so Isaac Newton was thinking about orbits, or he was thinking about gravity. Sorry, he's thinking about forces. The story goes, the apple fell on his head, and he starts to realize that gravity is a force. But according to legend, he also wondered, why didn't the moon that he saw in the sky fall like the apple did that was under the tree, right? The apple fell on his head because of gravitational force. Why didn't the moon fall because of gravitational force? And he thought about it, and he thought about it, and he came to his answer by thinking of this idea. He called it the Newton cannonball, okay, or we call it a Newton cannonball. So he said, what if I took a cannon and I put it on the top of a mountain, okay, and I shot it, okay? If I shot it with a certain amount of velocity, it will go a certain distance and fall to the earth, right? We can calculate that distance. We did that before, right? We know the equation to do that. And he said, well, what if I shoot it a little bit farther, okay? This time, if I shoot a little bit farther, it will go a certain distance, but the Earth's also going to curve a little bit, right? So it will go farther than expected because because of the Earth's curvature, right? We said, what if I shot this faster and faster and faster until it was going so fast that it actually orbited the planet? The cannonball was actually moving as fast as the Earth was curving. Okay, if that was the case, then the cannon would not, or the cannonball would never hit the ground, but it would actually just keep going and orbit the planet. And so he realized that the faster and faster he shot it, you could get so that it was outrunning the Earth's curvature. Okay, and then to a certain point, it would just exit the Earth, right? But he realizes this. He realizes this is what the moon is doing. It's not because it's not feeling gravity; it still has a gravitational pull, but it's actually because it's moving fast enough that it's in its orbit, right? It's moving fast enough that when it's falling, it's beating the Earth's curvature, okay, and moving towards the center, but it's still orbiting, okay? So if we go all the way back to this slide, okay, you may remember it from a few chapters, or sorry, a few podcasts ago, you'll see that, the velocity is in one direction, but the acceleration towards the center is another, which gives it this changing movement and makes it rotate around the center. Well, if you look at an orbit, right, Newton's cannonball, it's doing the same thing. It has some velocity that's traveling with, but it's also falling towards the center. But as long as it's moving faster than it's falling, then it can outrun Earth's curvature and orbit the planet. Okay, and so this is another really simple version, but this is our goal, right? Move fast enough that we orbit instead of hit the Earth. Okay, so we watched this video, okay, about how satellites orbit, and we also watched a video about can you see satellites in orbit just for fun. Okay, but again, that's the idea. Okay, this is with a tie-in. Okay, I'm going to go back to this picture. This is the tie-in to centripetal force and gravity and orbits, right? We learned how to calculate centripetal force, right? in these rotations? Well, guess what? We can think about the gravitational pull towards the center of the Earth as a centripetal force. Okay? And so not only can we calculate the centripetal force from finding the velocity and the radius and all that, but we can also calculate this force by using Newton's gravitational equation, right? G or F of G equals big G m1 m2 over r squared. Okay, they're two of the same things. Okay, they're the same idea. This force pulling in towards the object, but they're orbiting or rotating around the center because of their velocity. Okay, it's the exact same thing, just different applications. Okay, so that's the big tie-in between gravity, orbits, and centripetal force. Okay. All right. Then the last thing we talked about is we wanted to think about period. Okay, the time it takes an object to make one complete revolution of its orbit, or basically how much does it take, or how long does it take for an object to go around once. Okay, that's period. And we want to think about how do we calculate this period? How do we figure it out? Well, there was a man by the name of Johannes Kepler who really wanted to know this answer. Okay, and he did a ton of other stuff. He helped modify the heliocentric model. Okay, if you take an earth science class or an astronomy class, you'll learn a lot about him. But one of the main things is you want to know about period of these orbits. Okay, and we attribute him to what we call Kepler's laws. Okay, so Kepler, when he was studying the stars, he came up with, studying the planets, he came up with 3 laws. Okay, 3 laws that he noticed about the planets as they were going around this orbit that no one else had ever been able to discover or realize or state as clearly as Kepler did. Okay, so the first law, okay, again, these are kind of the very literal versions of the law, okay, but Kepler's first law says that the path of planets about the sun is elliptical in shape, with the center of the sun being located at one focus. Okay, so if you've taken a geometry class, you've probably learned about ellipses and focuses. Okay, if you haven't, don't worry about it. The main thing is I want you to realize is that Kepler was able to show that planets move in ellipses, not in perfect circles, like a lot of people expected at the time. Okay, that's his first law. Planets move in ellipses. Okay, the second law is, I think, one of his coolest laws, is he's able to show what speed the planets are going to move around with. And you can state it like this. So an imaginary line drawn from the center of the sun to the center of a planet will sweep out equal areas in equal intervals of time. Okay, so imagine the planet's going from A to B in its orbit. Okay, so here's the sun. It's going from A to B. That part of the orbit makes this triangle right here. Okay, that blue triangle. Okay, now imagine the planet's going from X to Y. Okay, that means it makes this green triangle, right? And so if the planet takes the same amount of time to go from A to B as it does to go from X to Y, then these triangles are actually the same amount of area. Okay, so you notice this blue triangle is really fat and short. This green triangle is really long and skinny. Okay, but they're the same amount of area. So what that means is that the planet took the same amount of time to go from A to B as it did from X to Y. So the planet's moving faster from A to B than it is from X to Y, because this is a short distance, this is a long distance. Okay, and so by using these different triangles, Kepler is able to show that the planets move at different speeds at different parts of their orbit. Okay, so that's really cool. He showed that planets had variable speeds, which hadn't been thought of before. Okay, and so first law was they move in ellipses. Second law, he could show the different speeds of planets. Okay, then the last law is kind of a lengthy one. Okay, that's the ratio of the squares of the periods of any two planets is equal to the ratio of the cubes of their average distance from the sun. Don't worry about that. The main thing you need to know is that, in other words, we can calculate the period of an orbit. Okay, we don't do this for this class, but just realize that he's able to mathematically show the period of an orbit. Okay, so again, the first law is he can show that the shape was ellipses. The second law is that he was able to calculate speeds. And the third law is that he was able to calculate the period. Okay? And so those three laws are huge to astronomy and to orbits, okay? And that is the end of the chapter, okay? So hopefully you're able to see kind of the connection between the centripetal force, general gravitation, and orbits, okay? They're all kind of interrelated. They all are just kind of saying the same thing, but just connected in different ways, okay? But hopefully that makes sense. Let me know if you have any questions, and thank you for watching.